Okay, so in this video, we're going to consider something called the radiation reaction. So if we think about it, acceleration of a charge causes it to radiate. Now, when the radiation leaves the charge, it takes away some of the kinetic energy. So the charge has a certain amount of kinetic energy. It then releases energy in the form of electromagnetic waves. So therefore, there should be a reduction in the amount of energy. So I would say that the kinetic energy reduces because of radiation. Well, a change in kinetic energy would then imply work, that there is work being done. And if there's work being done, then there must be a force being applied. So the question is, does all of our logic we've built up through classical physics match with what we're seeing in the case of a radiating electric charge? Not only that, but what you should see is if you had two particles, a charged particle which is then accelerating and therefore is radiating, and a neutral particle, then the neutral technically should not radiate because it has no charge. So therefore the charged particle should have some sort of force applied to it that the neutral particle does not. Or another way of saying it is that the acceleration for a neutral is greater than the acceleration for a charged particle. Okay, so it's as if they're, well, that's our logic so far, and we'll have to see where that takes us. One could think of this then, that charged particles, when they radiate, there is some sort of recoil force pushing back on that charge. So now that there's some sort of recoil right here occurring, that the charge is somehow radiating and then getting a kick backwards because of the actual radiation. So if we consider a non-relativistic particle, so V is much, much less than C, then the power would be mu 0 q squared, the acceleration squared, over 6 pi c. Okay. Now conservation of energy would say that that power is then equal to, say, force times the velocity, if it's a constant force. So assume that our recoil force is constant, and I'm going to call this rad, so a constant radiation force. And so the radiation force times the velocity of the particle should now be equal to minus mu 0 q squared a squared over 6 pi c. So in the end, but we do know for a fact that this is not the only amount of energy the particle has. When we worked out the electric field equation, there was the acceleration part, which is due to the radiation, and there was the velocity part, which is due to the fact that the charge just has this field attached to it. Okay. So what I guess I'm saying is that this radiation force that's feeling is only due to the energy that is associated with the actual radiation being expelled by the charge. If I now integrate to get the energy, so I'm going to integrate my power with respect to time, so I'm integrating from time 1 to time 2, then what I should get is minus mu 0 q squared over 6 pi c, the integral of the acceleration squared dt. Okay, so we're basically averaging the acceleration squared over time. So that integral I can write more formally as the acceleration dot into itself. Okay, so if we now integrate by parts, then what we'll have is v dot dv dt evaluated between the times minus the integral of v dot the second derivative of the velocity with respect to time, like so. Now, this first term here is going to be equal to 0 because v at a time t2 is equal to a v at a time t1, and a at a time t2 is going to be equal to a at a time t1 because I'm making the statement that I'm averaging over time. So this is the time average, and since we're dealing with vectors, you know, the average is basically going to be 0. The vector could go left, the vector could go right. Okay. So if I now put this back together, what I get is the radiation force minus mu 0 q squared over 6 pi c times the acceleration, the derivative of the acceleration, a dot, is equal to dot v dt. So I basically took both sides, I took the right-hand side of that equation, subtracted from both sides, and I now get a 0. So integrate over this. So the most interesting aspect of this would be that this radiation force is equal to mu q squared over 6 pi c, the derivative of the acceleration with respect to time. Okay. So that's not really any force we've seen before. We've never seen a force where we look at the change in the acceleration with respect to time. Now this is actually called the Abraham-Lorentz equation. Okay. So one kind of aspect of this, which is kind of unresolved with this result, is the fact that if we were to, say, apply this to Newton's second law, like so, then what I would get is, so this change in acceleration with respect to time would be equal to 6 pi c times the mass over mu 0 q squared times the acceleration. Okay. If you were to integrate that with respect to time, you would get a time-dependent acceleration equation, which essentially says you would have some initial acceleration at time t equals 0, t over a time constant, and that time constant is mu 0 q squared over 6 pi the mass of the particle times the speed of light. So for an electron, what you get is a time constant of 6 times 10 to the minus 24 seconds. So it's weird that the acceleration then increases over time. And not only that, but it increases over time in an almost minuscule time scale of 10 to the minus 24. So this, you kind of have this thing going on where you have what's called acausal acceleration, which means that the particle starts to move, you know, and instantaneously before the force is applied. There is this time where the particle begins to accelerate, and in a time, constant of 10 to the minus 24 seconds, it's going to accelerate before that force actually is applied to it. So that seems unsettling, and so there must be some sort of physics underlying this that we don't quite know yet, and we'll have to investigate further. But for the time being, we're going to kind of stop there and just say that, just concern ourselves more now with the fact that this radiation that the particle is producing is somehow going to be slowing down its motion. It's going to be applying a force which is kind of this kind of braking force. It's causing the particle to lose kinetic energy. So in the next lecture, we'll go over an example of where this radiation is dampening the motion of the charge, and we'll model it in the simplest force that we can think of, and that is a spring. Everybody loves a spring. It's a nice linear force. It's an easy one mathematically to deal with. And so in the next lecture, we'll go over an example where we treat the charged particle as a dampened spring.